السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we will have the last lecture in probabilistic modeling. Okay, we covered so far a naive Bayes, and there is still one more probabilistic model which is very important, which is and it's commonly used in classification, which is called logistic regression. So let's see what logistic regression is. And we'll start with this one. I think you saw this one maybe many times. Okay, this is Perceptron, right? In Perceptron, we have, let me change this. We have an input vector, a feature vector, and we assign a weight for each feature. We get the weighted sum, and then we use a step function. Okay, and the predicted value will be either 0 or 1. Based on the weighted sum. So if the weighted sum is positive, then it will be 1. If it's negative, it would be -1 or 0, whatever the convention that we are using. So that's Perceptron. Logistic regression is very similar to that architecture, to that structure, okay, except with one modification. And that modification is because that we want to get a probability at the end. We don't want to get just 0 or 1 or -1 or 1. We want to get actual probability. Okay, a value between 0 and 1 that will estimate our confidence or that classifiers believe that this example belongs to the positive class. How we will get the probability is to change the step function into what we call a sigmoid function. So if you look at the difference between these two slides, you will see that the main thing is that we changed the step function from Perceptron into sigmoid function in logistic regression. That's the only difference, but it is a big difference. As we will see, it will change many things. So what is a sigmoid function? Still we have a weighted sum. So this is the weighted sum as we do in Perceptron. But the weighted sum, instead of going into a step function, it will go into what we call a sigmoid function, which we denoted by the sigma symbol here. So Z will be an input to the sigmoid function, and the output of the sigmoid function is the actual predicted value from the logistic regression classifier. Now the question, of course, is what is the sigmoid function, right? So the sigmoid function is the function that you see here on the slide. First, why is it called sigmoid? Because the shape of it is very similar to the S letter. Okay, it's called sigmoid, and also it's called logistic function, by the way. That's why it's called logistic regression classifier. Okay, this is the word logistic here. Now, this function, as you see, takes as an input any real value, either negative or positive. Okay, from -infinity to infinity. So any real value, and what will be the output? Look at the between 0 and 1 always. Okay, always between 0 and 1. So it is convenient to deal with the output of that function as if it is a probability, because probabilities are between 0 and 1, right? So we can deal with that number as a probability. So this is the first thing. Second, you will see that as we have extreme values in the negative side, it will approach 0. Extreme values on the positive side, it will approach 1. When the input is 0, we'll get 0.5. The formula of the sigmoid function is what we see here. It's 1 over 1 plus e to the power minus z. Z is the input. So let's try and see what will be the value for specific, what will be the output value for specific input value. What if z is 0 from here? So e to the power 0 is 1, so 1 over 2 is 0.5. So when z is 0, the value of the function is 0.5. Type, if z is infinity, e to the power minus infinity is e to the power minus infinity is 0 or 1. Type, here e to the power minus infinity is 1 over e to the power infinity, right? So what is e to the power infinity? Infinity. 1 over infinity? Okay, so this is 0. So 1 over 1 plus 0 is 1. So when z is approaching infinity, we'll get 1. Type. If z is minus infinity, so e to the power minus z will be e2 minus minus infinity, right? Which is minus minus infinity is what? Is infinity, right? So 1 plus infinity, still, okay. 1 over infinity, 0. So when z is minus infinity, we will get 0. Okay, so this is the sigmoid function. Another thing about the sigmoid function, as you will see, it is kind of linear around 0. And when the input value is 0, the output of the function is kind of linear, but then it will approach 0 from one side quickly or 1 from the other side quickly. Okay? Is that clear? Do you understand now how the sigmoid function works? Okay. Now, let's get back to logistic regression. So back to the architecture here. So this sigmoid function is applied on the weighted sum. So based on the value of the weighted sum, of course, the value of the weighted sum, does it have to be between 0 and 1 or minus 1 and 1? No, it can be any value. Okay? So whatever the value that we will get as a weighted sum, it will be converted into value between 0 and 1. Okay? Which we will consider it as the probability. Okay? So the basic or the key property of the sigmoid function is that it's called squashing. It squeezes or squashes any input value into value between 0 and 1. Give me any value, I will put it between 0 and 1. I will convert it into a value between 0 and 1. Type. Now let's get to prediction. How we'll do prediction? We will, as you see in the slide here, and as we saw in the in Perceptron, the output value here is the predicted value. So y hat is the predicted value. In this case, we will consider it the probability that the class is 1 given the input x. Okay, so that's the predicted value, which is the sigmoid applied on the z or the weighted sum, which is the sigmoid applied on the weighted sum is wx plus b, right? So we'll just substitute in the sigmoid function, substitute z by wx plus b, we will get this. So this is 1 over 1 plus e to the power minus wx plus b. Okay, with me so far? It's just substitution of what z is in the sigmoid function. Is it guaranteed that this value will be between 0 and 1? Is it guaranteed? Why? Because of the sigmoid function. Any value that we will get from here, it will be between 0 and 1, the output of it. Okay? Right. Now, remember, or maybe you noticed, Perceptron was a binary classifier, right? Logistic regression also in its simplest form, which we will study in this course, is also a binary classifier. So we have two classes. So this is the probability of the first class, the positive class. Okay? Then what should be the probability of the negative class? 1 minus that probability. So 1 minus y hat is the probability of the 0 class or the other class given x, which is 1 minus the sigmoid of the, because the y hat is the sigmoid of sigma of z, right? So this will be 1 minus sigma of z, which is 1 minus sigma of wx plus b, which is this one. Okay? If you add these two, of course, you will get 1. Now, another property of the sigmoid function that we didn't talk about will be clear with the following question. Let's say that the sigmoid value for the when z is 2, let's say that this is like 0.8, right? Type. What is the sigmoid value for minus 2? 1 minus 0.8, which is 0.2. Okay, so that's another property of the sigmoid function. Okay, so the sigmoid of any value is equal to 1 minus the sigmoid of the negative of that value. Okay, it's not negative of that. So and that's applied, of course, of anything. This is for 0.4. Let's say that this is 0.95. Then sigmoid of minus 4 is 1 minus 0.95, which is 0.5 or 0.05. Sorry. Okay, so that's another property, and we write it here. So 1 minus sigma of z is sigma of minus z, or sigma of z is 1 minus sigma of minus z. Okay, the sum of them is 1. Sigma of z plus sigma of minus z equals to 1. Right, where is the prediction here? What is the actual prediction? So we know now how we compute the probabilities, right? Right, how can we predict a label given an example? Yes, so we get the maximum, okay, of them. So the predicted label will be 1 if y hat is greater than 0.5, because that means that y hat is greater, of course, than 1 minus y hat, and it will be 0 otherwise. Okay, so that's the predicted label for any given example. Any questions so far? Everything is clear? Type, what is remaining now? Khalas, we are done with logistic regression. Why is it called regression? No one asked me, actually. Okay, it is called regression because it's similar to linear regression. I think you studied linear regression, I think, in maybe numerical analysis course. Okay, and if you remember in the beginning of the course, we talked about regression tasks and classification tasks, right? What is the difference?
Regression gives a real valued number.
Yes.
Classification is one of the labels.
Yeah, so regression gives us a real value. Classification is a discrete value. Okay, it's one of preset or predefined labels. Okay, but this is called regression because it's similar to linear regression, but it is not regression. Okay, it's a classifier. That's always a confusing point. Logistic regression is not doing regression; it is actually a classifier. Okay, and it's the form that we study in this course. It's a binary classifier, but there is a way to make it a multi-class classifier, but we don't have time to cover it in this course. Because the way that it works, it's similar to linear regression. Okay. Okay. Any questions so far? Right. Here's an example. Can you please pick a piece of paper and tell me what will be, for this example, what will be the predicted value and predicted label? Any values? What will be z? Z is 6. Okay. How did you get it? Yeah, so that's so z will be wx plus b, right? B is 0 here. So wx is 1 times minus 1 plus minus 1 times 2 plus 3 times 3. That will be 6. Okay, then, yeah, the sigmoid of 6, it would be 1 over 1 plus e to the power minus 6. What do you expect? It's very close to 1, right? Because it's on the positive side, okay? And it will be something like 0.99. Did you compute it, actually? Okay. Okay. Type. Any question about this? Type. How about y hat? Y hat. What is y hat? Y hat actually is sigma of 6, right? Y hat, the predicted value. Remember, y hat is the probability that y is 1 given x, which is this value, which is the sigmoid of 6, which is 0.997. Type, how about the predicted label in this case? 1, of course, because this is greater than the other probability. Type, what if B is, okay, let me, oops. What if B is -7? So what will be Z in this case? -1. And what is sigma of -1? 0.7. Okay, sigma of -1. Okay, if you remember the shape, okay, the shape of the sigmoid, this is 0.5, and it appears when Z is 0. Okay, now Z is -1, so we would expect it to be below 0.5. 0.26. You agree? Anyone computed? Type 0.26. Type, how about Y? This is Y hat, of course, right? Type, how about the predicted label in this case?
0.
It will be 0. Okay, it will be 0. Type, any question about this? Any question so far? Everything is clear? Type, what is remaining? Are we done with logistic regression? خلاص? Yes.
This y hat is the label or the
Y hat is not the label. Y hat is the predicted value, which is the probability. Okay, and from the probability we get the label.
yeah, but what's the notation of the label? Y?
We don't have it. We don't have a notation for it here. No, not Y. No, no. Y is the actual label, the class. Okay, the actual label. But Y hat is the predicted probability. Okay, there's no symbol for the predicted label here. The number of features. Any questions? Type, what is remaining? You said yes, right? To type, tell me how we will get the model. Where is the model itself? WX plus B is the model? لا ولا حتى it used to be. What is the model? What طيب يعني forget about logistic regression. If I told you in machine learning, here is a model. How is it represented? Any model by the parameters. Okay, يعني I try to يعني مش عارف يعني you should memorize it for now. Okay, any model is the parameters, right? What are the parameters here? W and B. Okay, طيب. Did I tell you how we will actually learn the weights and the bias? No. Okay, I told you how it works, how we can predict once we have the weights as we have in this example, how we will predict a label, right? But I didn't tell you how we will learn actually the weights and the bias. Okay, so what is remaining is learning. Learning what? The weights and the bias. Okay, the model parameters. Type. Let's see how we will choose the values of the parameters, or how we will learn actually the values of the parameters. Let's say that we are in training, right? And we are given an example, a training example. We know its actual label, right? If we tried with the model, let's say that the actual label is 1. What do we want to get? What do we want to predict? What should be the predicted value for that example? The highest possible, right? So we want to be actually 1 or closer to 1. So when the true label is 1, we want to maximize the predicted value. The predicted value will always be between 0 and 1, right? So when the correct label is 1, we want the predicted value to be the maximum possible. Type, what if the true label is 0? We want it to be the minimum possible, right? So we want, when y is 1, we want y hat to be the maximum possible. When y is 0, we want y hat to be the minimum possible. or we can say it in a different way, 1 minus y hat to be the maximum possible. These are equivalent, right? Okay, now we want to learn the parameters so that we can maximize the probability of the correct label. We want a function, we want to maximize a function that will give us this. When y is 1, it will give us y hat. And when y is 0, it will give us 1 minus y hat. Okay? And we want to maximize that function. So, if we remember that y hat is the probability that y equals 1 given x, then we want to maximize y hat when y is 1 and 1 minus y hat when y is 0. So if I represent this in a function, then our goal is to maximize that function. Right? Are you with me so far? Now, here is a function that does exactly this. It's y hat to the power y times 1 minus y hat to the power 1 minus y. Now let's see if it actually gives us what we want. Now we want a function that will give us y hat when y is 1, right? So let's put y to be 1 here. What will we get? So y is 1, so this will be 0. So this will be what? No, 1, right? And y is 1, so what we will get is y hat. And this is what we want, right? When y is 1, we want y hat. We get y hat. Type. Let's say y is 0. Y is 0, this means that this is 1. And khalas, this is 0. Then it will be 1 minus y hat. Okay? So this function gives us exactly what we want. It will simplify to y hat when y is 1 and 1 minus y hat when y is 0. I was about to ask you. You saw this similar to this before, which is the likelihood probability function of Bernoulli distribution. It's exactly this. Okay? Because we have two outcomes there, we have also two outcomes here, which is 0 or 1. So it is actually the Bernoulli function, similar to Bernoulli function. Type. Then, if you are now convinced that this is the function that we want to maximize, then we need to think about how to maximize it. Alas? Following with me? So this is now the function that we want to maximize. So we will choose the weights and the bias that will maximize that function. That's the strategy of the training or the learning phase. Okay? We want to get the weights and the bias that will maximize that function, which gives us the probability of the correct label. Right. So the goal is to maximize the probability. We want to maximize this. This is what we saw in the previous slide. Right. Now, usually when we maximize a function, we want to get the values of the parameters of that function, right? That will make that function maximum. It is equivalent to maximizing the log of that function. If this function looks really complex, it will be much simpler if we just take the log, and we will get the same values of the parameters. Maximizing a function is equivalent to maximizing the log of that function. So we take the log. When we take the log of this, it will be log of that plus log of that, as you know from mathematics. And log of y hat y is y log y hat. And log of 1 minus y hat to the power 1 minus y, it will be 1 minus y. So the power will be just a multiplication factor times log 1 minus y hat. Are you with me? So this is just applying the log to this. It will make the expression much simpler. Okay? It's actually converted from the power factors to just simple factors. Simple addition and multiplication. Okay, type. Now maximizing this log function is equivalent to minimizing the negative of that function. Any function, by the way. If I want to maximize that function, it is equivalent to minimizing the negative value of that function. Okay, because we just multiplied by the negative, so the sign of the value of the function will be converted from positive to negative and negative to positive. So maximizing this is equivalent to minimizing the minus of that function. Okay, so now our goal is to minimize this function. Okay, this function is called cross-entropy loss function. I think you heard about loss function before, right? What is the goal of, or the objective of a loss function? It gives us an indication of the error, right? So we usually minimize it. We want the error to be minimum as minimum as possible, right? Time. Let's see if we really see this, or we can view this as a loss function. Loss function means it will give us an indication of an error, right? So let's see. If y is 1 and y hat, and we got y hat to be 1 or very close to 1, what should be the loss in this case? 0, right? That's the perfect situation. Should not get any loss in this case, right? Let's see what this function will give us. Let's substitute y is 1 and y hat is 1. When y is 1, then this factor will be 0, right? So this will be cancelled out. And here, y hat is 1, so this is 0, right? 0 times anything, it's 0. So 0 plus 0 is 0. So that's perfect, right? Type. Let's try when y hat is 0. What should be the loss in this case? It doesn't have to be 1, but it should be very high loss, right? Okay, very high loss. So you should expect at least a positive value, and it will be great if it's very high, because now we are doing the worst mistake ever, right? I mean, it's equivalent to the opposite, but it is the worst case. The label is 1 and the predicted probability is 0. It's not even 0.2 or 0.4, it's 0. There's no worse than that, right? So we should get the highest loss possible. Let's see what will happen. Y is 1, so this part is again 0, right? Because 1 minus 1 is 0, so this part is 0. Let's look at this. Y hat is 0. Log 0 is what? Is infinity. Log 0 is infinity. Minus infinity. Very good. There is a big difference, by the way, between infinity and minus infinity. So this one is minus infinity. Sorry, no, not 8. The big difference between 8 and minus infinity. So, and y is 1, right? So 1 times minus infinity? Minus infinity. And there's a minus outside. So the loss will be infinity. That's the worst loss possible. So this looks like a great loss function. When we are doing the perfect prediction, it will give us 0. If we do the worst prediction, it will give us infinity. And of course, you can also yourself try the other two cases, right? By the way, now we are here trying the extreme values of y hat, but y hat can be any value between 0 and 1, right? So in this case, if y hat is 0.3, what would we expect of the loss value? It will be positive or negative? Positive, closer to it will be high or low? It should be high, right? But it's not infinity. It won't be infinity. It will be a big value, but it's not infinity. Type. So that's a loss function, and it's called cross-entropy function, loss function. If you remember, I think we touched it quickly on entropy in decision trees, right? If you remember, entropy was one of the criteria. Entropy usually used to, or cross-entropy is used to get the difference or the distance or the divergence between two probability distributions. And here we have actually two probability distributions, the actual distribution and the predicted distribution. That's why it's called cross-entropy loss function. It's very well known, and it is actually one of the most widely used functions, loss functions for neural networks, as we will see inshallah in the next session. Type. Have we heard about loss functions before in the course? We heard about loss functions before, right? In which session? Huh? Which session we talked about loss functions? and minimizing loss functions. Optimization, yes. Which session was that? يعني 6 or 7 years ago. مش بعيد قوي. Linear models. Okay, linear models. So in linear models, we view the problem as an optimization problem, minimization problem, and we solved that minimization problem, right? How? How did we solve the optimization problem 6 or 7 years ago? Huh? This is not what I mean. Okay, whatever the shape of the function is, we had a minimization function and gradient descent. Very good. Okay, so we used gradient descent to find the solution for that optimization problem. Okay. Type. Before we do that, let's see the parameters. Where are the parameters here? We are talking about y and y hat, right? How is y hat is related to the parameters? Where is w and b here? The parameters are w and b, right? Where are w and b here? The loss function should be a function of the parameters, of course, right? Where are the w and b? It's y hat is a function of w and b, of course, right? So let's just substitute this. So this is what we saw in the previous slide. And this is just substituting y hat by the sigmoid of wx plus b, which is the relation, right? Y hat is the applying the sigmoid function on the weighted sum. So we just substitute here. Now it is a function of w and b, and we can, how can we minimize it? As we just said, by gradient descent. Okay, so we can find the values of the weights and the bias by gradient descent. Now, to apply gradient descent, what is the condition? To apply gradient descent to any function, it should be differentiable. Okay, this function actually it is differentiable, and even better, it is convex. It is a convex function, so it has a global minimum. We don't have a closed formula to solve it, so we will solve it by gradient descent. Type. To apply gradient descent on this, what do we need? Find the derivatives of the gradient. Okay, so the gradient of what? Of this function with respect to the parameters w and b. Okay, so of course we will not talk more about that because we already had maybe 2 or 3 lectures on this. Okay. Does that mean that this model is linear because we studied gradient descent with linear models? Actually, gradient descent, as I told you, it can be applied to any function. Okay, and it doesn't have to be a linear model. It's linear because we applied it on the loss function that is applied on a linear model. Okay, here we applied it on logistic regression, which is linear or non-linear. What do you think? Non-linear, of course, because sigmoid function is non-linear, right? So it is a non-linear model, but of course, gradient descent can be used to find the best values for any function as long as it is differentiable. Of course, it can start at local minima, but the good thing about this cross-entropy loss function is that it is convex. So we will reach the global minimum at some time, okay, depending on the initial value and the step size. Any question about this? Are we done now with logistic regression? It doesn't have to be no, yeah, always. Maybe yes, and we still have 5 minutes. We can spend some time talking about anything in the course. But with logistic regression, are we done with any information that we need to know how it works and know how we learn the parameters? That's all what we need, right, from any machine learning model, right? We need to know how it works, how can we train a model, and how can we use it to predict a label for any example. And I think we fulfilled both. So we are done with logistic regression, but still we have one concept that we will cover. Any question about logistic regression? Good question. Is perceptron different from logistic regression؟
هو أكيد different.
عشان بندرسهم صح؟ عشان درسناهم لوحدهم صح؟ بس you don't see the difference؟
لا I see the difference. بس أظن we counted twice.
طبعا these are completely different classifiers. Yes. Okay. There is similarity in their structure. Okay, but they are different classifiers. Usually logistic regression is one of the best classifiers, binary classifiers that you can use. Usually it is used as a baseline when we compare any new classifier. We should, especially in text processing, we compare with logistic regression. طيب, any other questions? Yes. هنخلص على فكرة, لازم نخلص اللي فاضل. في البريدكشن ماله البريدكشن؟ مش فاهم فين السؤال؟
يعني ده training case.
And prediction also, we talked about prediction, right? Once we have a model, we can use it in prediction. The example that you did manually, right? That was a prediction example, right? We assume that we have a model already, which is the values of the parameters, weights and bias, and we use it to make predictions. Any other questions about logistic regression? You understand now how it works and how it is trained? Okay. Type. The last point here in this session, it's not related to logistic regression in particular, and it's not also related to probabilistic modeling in particular, but it is one concept that we will at least apply on the models that we studied in probabilistic modeling session, which is the difference between generative and discriminative models. What is this? Let's assume that we want to build a classifier that will distinguish between cats and dogs in images. So if you give me an image, the classifier should tell you whether it's cat or dog, assuming that it will always be one of these two. Okay? So we need to train the classifier, right? In general, we need to train the classifier. So we need some images that have cats and other images that have dogs. Very good. Type. Now, there is one type of classifiers called generative classifiers. In generative classifiers, we will build a model for each class separately. So in our case, we'll try to build a model of what is in any cat image. So in any cat image, we'll see ears, eyes, whiskers, and other things, right? The things that will actually make it a cat. Okay? And then when we have an example, a new example, we will see what is the probability that this image was generated from that model. That's why it's called generative classifier. Actually, with that model, we can start to generate images of cats, because now we have a model of how cat images look like. Okay? You hear about now generative models that can generate images for humans and images of natural scenes. Okay? It's basically founded in this kind of classifiers. Type. Let's say that we built a model for cats. We also need to build a model for dogs, right? From the images of dogs, we built a model, and now when we get a new image, we will run both models. We'll see what is the probability that this new image is generated by the cat model, and what is the probability that this image is generated by the dog model. And of course, we will predict the one that will have the highest probability or will fit better. Okay, so that's the generative classifier. Okay, is that clear? Very, very clear. It is clear. Type. The discriminative classifier, on the other hand, will try to distinguish cats from dogs anyway, regardless of how or what in the cat images and what in the dog image in specific. So for example, it might pick up that all dogs or most of the dogs have collars. So it will ignore anything else and it will say, okay, if an image has a collar, it's a dog. Okay, so it will just ignore anything. It will focus on the things that will really distinguish these two sets of images, regardless of what else in the image exists. Okay? So this is called discriminative classifier. So in the discriminative classifier, we'll try to find one or few features by which we will be able to separate these two classes. But it will not build a model for each class, and it will not be able to generate new images. The job is not to generate images, is to separate or distinguish between these two classes. So we'll try to find the minimum number of features that will really distinguish between both. Even, and let me give you another example. If it happened that most or all the images of dogs have a garden background, a green background, maybe that will be a feature. It will pick up that feature. It will say, whenever the background is green, it's dog. It has nothing to do with dogs, right? Or maybe. But anyway, I think you got my idea. So I can generalize this by this diagram. The generative model or generative classifier try to build a model for each class. And then when we have a new example, it will try to find out which model generated this example. So if I have an example here, it will see if that model generated by this or that based on how it works, based on the models that we train. But the discriminative classifier will just try to separate the two classes, regardless of how we can model this class or that class. Okay, I hope that it is more clear now. Just the concept. We will not get into details here, but just the concept of what generative classifier is and what discriminative classifier is. Okay, any question? Type. Now let's see examples. How about naive Bayes classifier? What do we do in naive Bayes is to compute probability of a specific so this probability is the probability of a specific class given the example X. How did we do it? How did we do it? Naive Bayes. If you remember, we used the Bayes rule, okay, and we converted this into probability of X given Y. Okay, of course, this should be Y. Okay, so probability of X given Y times probability of Y divided by probability of X, and we ignore probability of X, right? So it is probability of X given Y times probability of Y. Now, if you really look at probability of X given Y, this is probability of generating X from class Y. So we are actually building a model for each class. Okay, and we are trying to estimate the probability that this example is generated from that class. So this is an example of generative or discriminative generative model. On the other hand, logistic regression, which we just studied today. What do? We directly compute probability of Y given X. We don't compute probability of X given Y and estimate Y given X from it. We directly compute probability of Y given X. Okay, so we don't build a model for each and we try to see what is the probability of generating the given example from it. We just compute the conditional probability directly. Actually, discriminative models are also called conditional models. So logistic regression is an example of discriminative classifiers. Okay, is that clear? The difference is clear? Yes. Any other questions? Do you understand now the difference between them? Do you understand how logistic regression works? Okay, with that, we are done with the probabilistic modeling session.